你就是这样就对，这样他们能听到。Hello Hello，可以啊，好，sounds good. Hi everyone, thank you for attending the seminar with Professor Jiajun Wu from Stanford University. Professor Jiajun Wu graduated from Tsinghua University as undergraduate student and later he got his PhD from MIT and he started his assistant professor job at Stanford University. And his main area is 3D vision and robotics. And uh, although at a very young age, his work has been cited over 40,000 times with H index over 80 times. And yeah, let's welcome Professor Jiajun Wu's talk. Okay, yeah, thanks for having me here, Moyu, and nice to see everyone. So I work on computer vision. So I heard we have a lot of experts in human vision here. So I understand very little about human vision. But it would be nice to just have a to see and contrast the differences between So here when I say visual intelligence, I mean machine intelligence, machine visual intelligence, and how can we build machines that can understand and interact with the world just like humans. One thing I want to emphasize is it's really working. Oh, maybe I don't. So so of course, if you look into AI right nowadays, everyone's training these large models and they're clearly very useful. And you want to leverage the power of data so as in these data-driven methods. But also at the same time, sometimes you wonder, is there anything about the knowledge of the world, right? So like physics and how they can be incorporated into these learning systems. And if so, in what ways? What are the mechanisms that we can integrate knowledge? So that's basically the theme of the talk. I'm going to talk about a few ways of our approach that has been trying to integrating these kind of physical intrinsics into data-driven, a large vision models or multimodal models. Okay, so we want to build machines that can perceive, right? See like humans perceive and generate, understand the world beyond 2D pixels. Now here I show you a picture of a lion, and you understand that we're seeing the picture of a lion because it has an underlying physical, we call it physical intrinsics, right? If you think about generative causal process behind this picture, why we are seeing the picture the way it is because there's an underlying the geometry. It has certain materials and textures and motions. And the process of taking these underlying object intrinsics and producing the picture, right, is a traditional subject in computer graphics, not like in rendering, but also more generally in physical simulation, right? So how can we take these physical properties and simulate what's going to happen and render, produce these beautiful pictures? And in some sense, you can argue that the vision or perception process is trying to invert this generation process, right? So that's why, in 20, 30 years ago, when people studying computer vision, they're all like computational neuroscientists who study human vision, like David Marr. They say, okay, vision as inverse graphics, right? So I'm trying to invert this process, and I can take a picture and infer the things you care about, right? Including geometries, materials, motions, and everything. And because there's, of course, this is an underdetermined problem, there's a lot of uncertainty in the things you cannot see, right? So you ideally want to also estimate the distribution of the properties you care about. Right? So we want to solve this problem now using all the AI tools, right? So they are very good at, once you have the data, then you can say, okay, image and language, then they can generate beautiful pictures from language, or they can put captions or annotations on images. So they can, once you have the data, they can learn very strong models that link these different data of different modalities. So the challenge here is, if I want to solve this problem, I want to take the image, I want to reconstruct other geometries and textures and materials and motions. Then the limitation or the challenge here is you actually don't really have that much data, right? So unlike images, videos, and language, where you can go to YouTube and download a lot of videos and have all the captions, right? for object geometry, for object materials, for object motion, you almost have no data. So now the challenging problem becomes, if I want to solve this problem, but without having a lot of annotations, right, how can I really still use AI and try to combine the two? So I'm going to introduce like two ideas. The first idea is maybe we can use, although we don't have much knowledge, much annotation about physics, physical attributes that we care about. We actually have a lot of knowledge about physics itself, right? So we can use these physical intrinsics as inductive biases for self-supervised learning. So what is going on is, I have all these observed visual data, and I want to have a neural network that try to infer the physical object intrinsics I care about, shape, materials, and everything. I don't have annotations here, but what I do have is some knowledge about how these physical properties are supposed to interact with each other, right? So these are the studies or findings from computer graphics or simulation, or more generally in physics, from the past decades, right? Because we understand light and object surface and geometry, how they're supposed to interact with each other, and how they're producing these pixels. So you do have knowledge about the interaction process or the simulation process. So although you don't have annotations here, if you're building these physical intrinsics as the intermediate representations and let it go through this ideally differentiable simulation process, then your goal can be now visually to reconstruct input image. And you can use this self-supervision, right? The reconstruction loss as the self-supervision to, in some sense, get you the object properties you care about it for free, right? So here now, okay, I don't have annotations on geometry or materials, but I know if I can estimate them correctly, then through this, physics-informed rendering process, I should be able to reconstruct input images. So this allows you to get some of these information for free. Okay, so let me give you some examples about how this can be done. So during training, you can do e-render or inverse process and simulation of forward process through self-supervised learning. You can train it on a collection of images and videos or from the internet, for example. And during testing, you can even just take the first half, right? You can just go from a single image and try to reconstruct or infer a lot of the physical object properties you care about. So some examples of that. So here, this is a paper that we did a couple years ago now. So we go from a single image. This is an image of a bouquet. And you can see that there's a bouquet has like 50 different roses. Right? So we asked this pretty fundamental question that is, okay, if I am, so what makes these roses they look similar, or what makes them have the same name, right? So if I compare, this is like a Pepsi can, right? So this is rose, that is rose, this is rose, right? What makes a rose, and what makes a Pepsi can not a rose? So what is really the underlying difference between these different objects, or between the fact that these objects belong to different object categories? So our observation is, fundamentally, yeah, these are like multiple instances from the same object category. But what really makes these different instances share the same name or belonging to the same object category and makes this Pepsi can belonging to a different object category is the fact that they actually share the same underlying distribution of object intrinsic. Right. So think about it as, for every rose, right, there's an underlying distribution that belongs to a category of roses of its possible geometries and textures. So what you're doing is there's some PowerPoint artifacts, which is annoying. But anyway, so what is actually going on is you can sample from this latent distribution, which is to be modeled, to be learned. But once you have learned it, you can sample from the distribution. You can get object rows of a certain shape with a certain texture. And then you couple that with extrinsic factors like lightings or camera parameters or poses. Right? So you're sampling a certain rows with its own geometry and texture. You're putting a certain pose under a certain lighting condition. That's why it leads to all these different observations of the roses, right? So they don't look exactly the same, but you understand, okay, yeah, they belong to the same object category. And the fact that a Pepsi can is not a rose is because it has a different distribution of its intrinsics. So now the question is, how can we learn and discover that latent distribution? You don't have to make any assumptions on what does that distribution look like. But only leveraging the fact that you assume, which is probably true, that these different objects, they actually share the same underlying distribution. It allows you to build a neural network or learning system this way. That is, you can sample from a latent code and through a neural network that tries to model the possible distribution of object geometries and texture. And you can let it go through, you can put that together with environmental extrinsics like the lightings or object poses. You can let it go through a differential rendering process. So you can take the geometry and and texture like a middle of the objects and put in certain lighting conditions in certain poses, and you can render the shape and appearance of the object, and finally get a picture. And your goal is, of course, to make this picture to be as close as possible to the real pictures, right? So this is what we did 3 years ago. So back then, we're not even using a lot of these latent AM methods like diffusion because they're non-existent. So we just used a very simple idea that is, okay, now these two images should look as similar as possible. So you can use a discriminator loss, right? If you're familiar with AI, there's this called Jiajun adversarial network. So you can have an adversarial classifier that tries to classify whether these two pictures are the same. And your goal is trying to make these two pictures look as similar as possible so that the classifiers cannot tell. Okay. But now you can, of course, use much better methods like the diffusion pliers. If you're familiar with those kind of things, you can do score decision sampling and different ways of incorporating pliers that has been trained on much larger data sets. But back then, right, even with this very simple idea, that they should share the inline distribution, and with the discriminator loss, which is relatively easy to implement. And what we can do is now you can go from just a single picture. You can actually do a lot. With the right inductive biases, you can do a lot from just learning from a single picture. So what you can do is, as in the bottom row, you can see the objects because you're learning the geometry and texture, so you can see it from different viewpoints. And second to bottom row, you can see it under different lighting conditions. You can change the lighting. And in the middle row, you can vary object because you learn the distribution of possible geometry. You can vary its geometry. You can sample different instances from it. You can see the object shape will change as well. So there's right. You can vary object shapes. You can see in different lighting conditions. You can see in different poses. Okay. So you may feel like, oh yeah, the results are not as sharp as possible, which is very true. But first, this was done. These are proper artifacts. But I want to but I should emphasize that first, this was done like 3 years ago. So the paper was published 2 years ago. So it was done 3 years ago. And now you have much better models, the AI models you can build out. But second, I think it's more important is you're learning everything just from this single picture, right? You just have one input image, and also nothing is pre-trained, right? So you're not taking a large pre-trained model, right? It's a cheating. You're training from scratch. So you just take a neural network, initialize it, and you just train it from scratch, all from one single picture, and you can do so much with the right inductive biases, right? So that shows like, okay, actually, by having the right inductive biases, that allows you to do a lot with very minimal data. Okay. So yeah, so this was done by my PhD student Intrinsics. Okay. Since then, we made some improvements. This is only for a single object category. So we wonder, object categories are not independent. Especially if you look at these animals, right? They share the same skeletal structure. So is that possible for us to learn not just from data of a single object category, but learn from data of many different object categories? So what's going on here is we collected internet images of 100 different categories of animals. But they're all quadrupeds. So there's no snake, there's no fish or anything like that. So they're all quadrupeds. But they do share the same skeletal structure. So our goal is the same, right? Can we reconstruct object geometries, textures, materials from a single image? Training on now a collection of images. But during testing, going from a single image, reconstruct the geometry, texture, and material of these individual animals. You have one model that's supposed to work on all these 100 different object categories. You can do generation sampling as well. So this, what we call is learning the 3D fauna from the web. So we have the internet web data, and you try to learn a model that works to reconstruct these intrinsics of these different object categories. And in addition, because these categories are not independent, and we assume they're all quadrupeds, so they share the skeletal structure. So we also try to reconstruct the skeletal structure as well. All right. So this was led by Jiajun, who is my PhD student, and Elliot, who was my postdoc and now is an assistant professor at Cambridge, UK. Okay, so going from one object category now to multiple object categories, and then a few other extensions we did is we try to incorporate a rigging structure, which means you go from an image, you will reconstruct objects and their skeletal structure, but in addition, you also reconstruct or try to infer the skinny weights. Skinny weights is basically, you have a skeletal structure, which means you have a number of key points, right, and their connections. But as skinny weights means, you try to also infer how, in what sense are these key points impacting the meshes, the vertices of the meshes, right? So how we can convert from these key points, what are the relative weights of these key points onto the vertices of the mesh, which means, if you then drag the key points, then the objects will deform, right? So you can learn to drag and deform the objects as well. Yeah, so this allows you to not only reconstruct the objects and their textures and their skeletal structures, but also you can edit the skeleton so that you can rig, just like move the characters. And similarly, we want to do it in a category agnostic way. So not just like learning for one model for roses and one model for something else. And in this case, we learn one model, and the model is not only just for animals, it's actually even for general object categories beyond quadrupeds. Now you have a model for fish. You want to make it work on fishes. We want to make it work on glasses, but you just have one model. So one model that works on all these different. So you have a shared structure. So it's just one model that works on quadrupeds, fish, glasses, man-made objects. Then you can infer the skeletal structures like the blobs and their connections and the weights. So how they're impacting the meshes, which allows you to edit the blobs and decode it so that you can see how the shapes are also being deformed. So the training on the model conceptually, of course, every model, when you implement it, it's kind of slightly different, right? Because you have to deal with slightly different data structure. But conceptually, it's very similar. You still do, we say physics intrinsics inform self-supervised learning or unsupervised learning, right? So what is going on here is, for the blocks, you sort of separate it into intrinsics, which are the things that really belong to the object itself, the identity, including the scale, the opacity, the embedded features, which captures like the detailed geometries or the possible embedding weights, and the scaling weights. And you separate that from the extrinsics, which is the pose and rotation, position and rotation of the blocks. So what you can do is you can say, okay, during training, or maybe you have objects that got deformed. So you can keep these identity vectors and these features, right? These are the embeddings, so the features that should be unchanged, kept intact. And these are the poses, but you only allow these pose variables to be changed. So then during the reconstruction process, right now, you should say, okay, I should be able to reconstruct objects with the same identity, but with a different pose, right? So it's like high school physics, right? If you go to high school study physics, you're like, oh, I keep the mass, I only change the friction coefficient. What's going to happen, right? Control variables. So you can control you can train on the data set of these animatable objects, but then for each object, right, you can change the mesh, move it a little bit, there should be the same object. So here during the training, you're doing the reconstruction, right? Self-supervised learning, where you also keep the identity, or you only allow the change of the pose vectors. So this allows you to learn separate representations for the intrinsic properties like object geometries and scales, opacity versus its pose. It allows you to do the rigging. So here is some more results. Adding the blocks, you can have an input of the bear. You can move part of the bear, the leg to a different pose. You can scale it to make it larger. You can remove a blob so that one of the legs is missing, or you can even add, generate, copy another leg, whatever, generate some of these out of the distribution object geometries as well. Yeah, so this was also led by Elliot, who was my postdoc, and two PhD students. Chen is my PhD student. Guang Zhao is a PhD student now at Cornell. Yes.
A comment how those blobs are related to Gaussian splattering.
You
also have some blobs.
Gaussian splats, mostly you can think about it as it captures the radiance and there's a density. So it sort of gives you a little bit of geometry, but the connection to geometry is not explicit. And it was mostly just for modeling the appearance, so that the radiance, right, after you go through this rendering, then it matches the visual input. It was primarily for novel synthesis. And here, the blobs, I think the most importantly is associated with the scaling weights. So that allows you to have a mapping from the blobs to the positions of the mesh, which is I think I'm not, but it doesn't model appearance, right? It doesn't have the color. So I think they're just like, of course, there's some kind of conceptual connections, but the purpose are very different.
So you just mentioned, yeah, so the Gaussian spread, there is no edge between different versions. So it is very hard to identify the Gaussian spread in order to influence the geometry. But you said, so the problem for the block is like, it doesn't have any appearance information, it's just based on the geometry. As far as I say, it's more like the key point or the cluster for different mesh part. By editing the block, you can actually editing the mesh. Like how do we have like the 2D Gaussian spread, which link the Gaussian spread with the mesh? Because like Gaussian spread is really to squeeze the one dimension, which is the net dimension, to have the 2D mesh. So have you ever thought to combine this block with like the 2D Gaussian? So you will have both editing for the appearance and also the geometry.
I don't understand, sorry, how the 2D Gaussians have any connections to meshes?
Because in the 2D Gaussians, what they try to do is like the link like the 3D.
Well, I understand what 2D Gaussian is. We use it a lot in some other work, which I'm not going to talk about, but
yeah,
but I don't understand how it connects to meshes.
Because in the 2D Gaussians, in the mesh reconstruction process, the aim of the 2D Gaussian is to reconstruct the mesh of the object. So what they try to do is like the duty iteratively. First thing you will have the Gaussian, and then you project it to a mesh, you reconstruct the mesh, and then you resample the point from the mesh, you will get another Gaussian spectrum, and if you optimize it iteratively, or you will have like the perfect mesh and perfect Gaussian. So which means like you also have the direct relationship with the mesh.
I'm not sure if I agree with that. Okay, there are too many things to entangle here. So first, I guess 3D Gaussian, there's only one definition of 3D Gaussians.
Yeah.
And 2D Gaussian, there are probably 5 different papers that claim they're doing 2D Gaussians, where there's circle representations, and there's like some different ways of parameterizing 2D Gaussians. So maybe we're talking about different things.
Yeah.
But in my understanding, I think for 2D Gaussian, they always want to sort of map it to the surface of the object. But a surface object is very different from the mesh, because mesh has very totally different properties, right? It's like it's watertight and has vertices, and I think it's just like fundamentally different representations. So I think there's some similarity between these two representations, but I wouldn't say there's a way that you can easily convert. Maybe put it this way. Now, I don't think, for example, 2D Gaussians is better or easier than 3D Gaussians if you want to convert a mesh out of it. Right. That's my feeling. So in that sense, I'm not sure if your question really stands. But maybe we're talking about different 2D Gaussians.
Yeah, maybe we're talking about different 2D Gaussians. Yeah.
But if you're really asking about, if you can put textures on it, it's in the case that our earlier work is already putting textures on it, right? It's just like in the block in the editing part, we focus on, okay, if you just edit geometry, so we just only show the geometry editing, but there's no reason that if you can have texture here, there's no reason you cannot have texture there. Okay. A related thing we did is we tried to have build a data set. So there has been a lot of the 3D object data sets that people try to collect from the internet. And the most well-known one is called Objverse, which is from AI2, the Allen Institute of AI from Seattle, where they try to crawl and almost all the possible 3D models you can find from the internet. So it's called Objverse extra large. And then we kind of filter them, and then we identify what will be the subset of the objects that are animatable. So we now have data set of these animatable objects that you can train and develop these models from. Okay, so up to this moment, I think everything I talked about has been like, oh, I'm trying to do encoding, decoding style of learning object visual structures in a self-supervised learning way. And as I will mention later, I feel like these kind of approaches over time, we realized there's quite some limitations. So I was almost like, okay, this is probably the end. But turned out one of my students, Chen, he's very good. And then he did something that's surprising, that's really surprising to me, is I think he pushed this line of work to another level of difficulty and solve an even harder problem, which is he's trying to model not only, up to all the rigging that we did, right? And it's model a particular kinematic state. It was like, you can change object to a certain pose, and then you can say, oh, you can change some of the physical parameters or kinematic structures, but you just render a particular state. Right? I can move here, I can move here. but it is not really learning or modeling what is the possible kinematic space that every object supports. Right, for example, I think this is a nice example. For this object, right, I can do this, I can do that, I can do that. I can do this, I can maybe even do this. So this is the possible space, right? The kinematic state space that it supports. And if I try really hard, I can maybe break it, right? But there are things that I cannot do. For example, I cannot have this microphone penetrate, no matter how hard I try, I cannot have it penetrate into the base, right? So there are, just like humans as well, right? There are certain things that I can do. I can do this, I can do that, but there are a lot of things that I cannot do, right? So the poses, every particular embodiment of structure supports for both, creatures or for man-made objects is limited. So we have always been modeling this individual state. I have never really tried to consider, we means just me, not the community, my group. We have never considered how to model the kinematic space, and can we learn to discover the entire space as well? So we have a distribution, right? Not just for geometry of a texture, but also for the possible states that the object can reach. So this is what he did in this latest work, which is not even published yet, just submitted. So the goal is there's underlying distribution now, the space, but this is the space for the possible kinematic states. So you want to learn not just the individual state, but you want to learn the space. So, if you sample it from a point within that space, you get a possible deformation of the object, like in the case of Newton's cradle, right? Or maybe one of the balls is like up in the air, these kind of things. And if you sample it outside of the possible distribution, you get random shape, right? So which doesn't correspond to a realistic possible deformation. So now the question is, how can you discover this possible deformation space? And so in this particular case, my dad is Chen, and this work called neural object kinematics. So using neural network to discover a model dilation distribution. So what we're doing is we can take a static 3D object, and we try to go through a feed-forward prediction method. It was trained through some kind of reconstruction, similar as before. But during testing, you just take the feed-forward encoder prediction part, and which maps the object into a latent space. And then you can sample from the latent space. It's going to give you the possible plausible deformations of this object. And you also want it to be category agnostic, so you can take any object and sample its possible deformations. And the way you do that is also conceptually very, very similar. Now you have a encoder-decoder training framework. So you have a mesh, which is a static mesh. And during training, right, you can see objects may deform in different ways. So you have a deformation field. What we're trying to learn is you can have a conditional VAE or a variation autoencoder. So you have the condition mesh as the condition to the VAE. And you're encoding it into a latent distribution, which you need to sample from, with the goal of, you sample from it and cover possible deformations of the object. At the same time, you learn instance-specific encoder, which only takes a static mesh as input, right? So because during testing, you don't have a possible deformation. During testing, you only have a static mesh. So you want to also have an encoder that only takes this conditional mesh, which is the testing input, into a latent distribution as well, right? And then you can sample from that as well, with the hope that this also captures the possible deformation of the object. So, and then if you capture deformation, you can decode it, and you should be able to reconstruct the deformation. So the way you do that is, you sort of decoder, and now you have two different losses. The first is a reconstruction loss, right? The same as before. You're reconstructing the output, input, and here the input is one possible deformation of the object, right? So you're reconstructing this deformation so that it matches the deformation observed during training. And second is, of course, the VAE themselves, they have like, if you're familiar with VAE, they have regularization loss here as well, so separate things. But in addition, you have additional payload divergence loss, which try to make the distribution of this distribution, which is the encoder only from the static shape, and the distribution that got encoded from the conditional VAE to make them to be as close as possible, right? Because during testing, you don't have, during training, you have static object, you can train and deform it, you can play with it, right? For example, you use our animate data set, the one we collected earlier, you see objects, you can deform it. So during training, you have a static shape, you have the deformed shape, you can use it to reconstruct the deformed shape. During testing, you don't have any deformed shape. You only have a static object, an object you've never seen before. But you want to encode it, you got this distribution, which during training has been trained to approximate the possible deformation space of the object. And you can sample this from this this distribution, so you don't have anything below now. But you can still decode it and get a possible deformation from even a static shape. I hope that makes sense. No. Okay, so it works actually surprisingly well. A very simple idea. It works surprisingly well once you have the right data set. So this is the output, right? So these are examples of, the model just supports, going from, you go to static scene, this is the office, right? The model allows you to interact and basically deform with almost all these diverse objects you see from. And this is the office, and then I have a kitchen scene as well. And you have that's a bathroom. This is a kitchen. Sorry. Yeah. Well, it was a bathroom, and this is a kitchen scene. Okay. I think people may say, okay, that looks great, but then all the objects here are like, you can see this in simulation, right? So you're like, oh, maybe these objects are so rigid, right? So how does it work if it's not in a simulation? So one thing we did is you show that it can actually generalize to real world. And the way you get it is very simple. You can take your iPhone, right? Now iPhone, they now allows you to do 3D scanning. So this is one of our students and trying to scan his own apartment. Right, he's just like taking a video, and the iPhone will automatically scan your apartment for you. Of course, he didn't touch any of these objects, right? So the objects here are all static. And you can see from the scanning output, right? The meshes look not very good. This is the iPhone's problem, not our problem. Now, iPhone gives you some crappy scans, but even with these crappy scans, right, which is very different actually in some sense from the beautiful objects we train on, the system still allows you to animate and interact with all these different types of objects, even from the scan output by your iPhone. And here is one more example of the scanning from his own office. So the system generalized almost perfectly. Again, the pool mesh is all from iPhone, not our problem. But even with these imperfect meshes, right, you can still animate and interact with them.
One question.
Yeah, I think there's a good place to take questions. Yes.
Your training, how the default field is obtained is from 3D scanner or something like that.
For example, you can use
The ground truth for.
Yeah, for example, here, right, you can use like this data set, looks like it, the animated data set, which is filtering from larger 3D object data sets like Observerse. You get from these larger 3D data sets of Observerse a subset of the objects which are animatable. And and they basically tell you what are the joints that you can animate, what's the degree of freedom that is supported. So then where these annotations come from, they're mostly from the artist.
We animated through a model or by.
So you train all these for example, the synthetic. You can say it's synthetic, the objects that are collected from the internet. Yes.
So I suppose like the this is my legacy. Maybe or something else.
There's no scene here. Motion, there's just an object, right?
It's an object.
Yeah, you can say it's an object deformation field. I think scene flow to me means something that's very different. But there's an object, it's a 3D deformation.
3D, yeah. And I have another question. It's like, because it's based on information field. Have you ever think about the cases with color apples, we will open things? That because it's kind of information.
I mean, let me think about what's the right way to answer a question. okay. In short, I would say no. We have not considered that kind of case because it requires the changing topology of the object, and we're not considering that right now. Yeah. Okay. Yes. Yes. Like this one or the synthetic one? Oops.
The current spring, the shadow behind this, yeah, just over there. This one, yeah, the
Yeah.
shadow will change it, so.
Oh, the shadow is because, we just, we only model object geometry. And so this is the rendered scene, right? So you change object geometry and the graphics image render the shadow. In this work, we only focus on objects. There's no modeling of the shadow. So it's an object-centric model.
I think it's consistent with the work, so if the screen changing and the shadow should be changed. So it's the capability to learn from the training data, right? So
No. Well, in some of my later works, we can talk about that. But here, let me emphasize, this is object-centric. You only care about objects, right? So you don't model the shadows or anything. You just model the object geometry and how it deforms and the texture how it deforms. So here, of course, this is and then we render it right into a video. So you have object geometry, you interact with it. I was like, okay, if you interact with the objects will deform. But you want to produce a demo. Produce a demo, you have to render it. Right, you render it, so there's a fixed lighting which we artificially set, or maybe assume there's a light over there, right? And then you deform the objects, and then you can just render the objects with this deformed geometry in a graphics engine. And the graphics engine do ray tracing and all these, right? So take care of the shadows, but it's not an output of our model. Yeah, but in some of our work later, we focus more on the video stuff. We do assume, let's say, video generation methods, they will take care of the model, take care of the shadow, but not in this work. Okay, in this work, there's no modeling of the shadow. It's just the object. It's object. Everything here is up to this moment. Everything is object-centric. Okay. So this is the first idea, which I think I spent more time than I expected, but speed up. So we try to have inductive biases in the middle, and then we do self-supervised learning. You can see that it does require a simulator. The simulator can be neural network or can be some differentiable simulators, but they also come with some constraints. Right. So for any of you who you also use simulation in your work, I assume maybe in biology or medical, you use a lot of simulators as well, simulating human bodies or human eyes or something. So it has a lot of constraints. Right. First, to put it in the loop of training, it has to be differentiable, right? Because you have to do forward, backward. If you're familiar with neural network training, you have to do backpropagation. And backpropagation requires everything to be differentiable. But there are a lot of simulations that are not necessarily differentiable. And second, simulators may not be very accurate, right? There are things that we don't really know how to simulate. So if you require simulators to be very accurate, you look into more specific domains. And third, because it's also in the loop for training, you have to make it very fast, because sometimes you can do simulation very well, but it just takes a long time to get accurate results. Right? If you look at, atmosphere, right? So if you want to simulate how climate, right? You can do very accurate climate simulation, but it takes hours, right? To give you maybe the simulation of 1 minute or even half a minute. But if you want to have a simulator in the loop of neural network training, you want the simulation to be very fast, which is every forward pass takes probably less than 100 milliseconds. So that also constrains the type of simulation you can do. So all these constraints lead to some resulting issue, which is the objects, the case, for everything we showed before, only works on cases with certain assumptions, right? Including, in particular, it's mostly like single object, it's object-centric. And sometimes you have to make even more assumptions, like there's a clean background, or there's certain lighting conditions, or you only work with rigid bodies or something like that, right? So some of these are getting more or less addressed, but there are also a lot of constraints that remains. So this is also the time that we realize, okay, yeah, the foundation models, right? So including large language models and vision language models, but in particular, video diffusion models are getting a lot better and are very popular. If you can generate beautiful videos just from language descriptions, then these models must have learned something about the physical properties. Even if they're not perfect, they must have learned something out of it. So now the question is that possible for us to extract as much physical properties as possible from these pre-trained models? So in some sense, in parallel, we have been exploring the second idea, which is instead of having intrinsics as intermediate representations, we take these pre-trained models, right? Think about it as a video diffusion model, as a very large encoder decoder model. And it's not exactly doing that, but think about it as a pre-trained model. And it can do so much. So can you distill or extract as much physical object properties as possible from this pre-trained model? So that would be the second idea. So one example here is also led by Chen, but it was from last year. He did this work on distilling physical object properties of arrows. But we talked about geometry, texture, material. We talked about possible deformations. One thing we didn't consider in the previous work, which also belongs to object intrinsics, is its lifespan, right? Because the rows can grow and can wilt. So to what extent can you distill a blooming rose or a wilting rose from a pre-trained video diffusion model, so that you can see the roses from different viewpoints under different lighting conditions, but you can also see the growth process and the wilting process of the rose, right? So that is, I would say, solving a bit harder problem. The method is actually turned out to be really complex, so I don't have time to go into detail here because this is the first time when we're doing some kind of distillation, and we designed a very complicated pipeline that has to build on top of image diffusion models, video diffusion models, and visual language models. So it's pretty complex. But later we simplified it. Yeah. It works not only on roses, it also works on, let's say, other dynamic processes such as baking a bread, right? You can see the bread, you can see it from different viewpoints, different lighting conditions, but you can also see the baking process. Yeah, but we're trying to simplify pipeline and have some interesting ideas, which happy to share later. So today I don't think there's time. But let me talk a bit more about, I think that's something that's even more exciting is, okay, we talked about object geometry, texture, material. We talked about their kinematic states and the lifespan. One thing we didn't mention so far, which is very important, is now how you can go finally from kinematics to dynamics. So what's the difference between kinematics and dynamics? It's like, kinematics is like given the drawing positions or state, right? So you can compute the drawing positions, right? Okay, but it doesn't tell you how the object is going to respond to external actions, right? So if you have a current kinematic state and then have applied action, then what's going to happen to the object, right? So you haven't really modeled dynamics. And to model dynamics, fundamentally it requires you to now have a detailed understanding of not just geometries and skeletal structures, but also really the physical properties, right? So if we want to solve this even harder problem, you can do action condition dynamics prediction of 3D objects. Then how can we, let's say in the case of a rose, right? So not just like it grows or different lighting conditions and stuff like that, but also, how the rose will respond to the external perturbations, right? I can apply the action, I can drag the rose and see how it will behave or react to my actions, respond to my actions. And because it's action condition prediction, you can apply different actions, right? So you can go from a static rose, you can interact with it in different ways, and it should all respond pretty naturally, right? So this is the next problem, and an even harder problem we want to address. And to address this problem, it really requires you to have physical properties, understanding physical properties. Now, geometries, textures, they're all physical properties too. But here, maybe we're looking to a more narrow definition of physical properties, which is like, mass and friction. In this particular case, we focus on this thing called stiffness, which is Young's modulus, right? How much the object, how stiff the object is, so that once you have a good understanding of the stiffness, you should be able to respond and model, how much the object is deformed with your external perturbations. So it turned out, people may feel like, oh, it's just one number. If it's just one number, then I just, randomly assign them or sample a few times, maybe I'll be lucky. And it turned out it's not very simple because, any real objects, especially for flowers, right? It is not homogeneous. It's not like every part of flower is the same, right? The petal of flower, the stem of flower, right? It has very different physical properties. So not just one number. It actually it's fundamentally there's a physical field that you have to model in addition to the appearance, right? So if you randomly sample physical property, let's say I use some heuristics and I just apply some general stiffness to the objects, then you're going to get simulation results that are very unrealistic, right? So just doesn't look right. So it shows that actually getting good estimation of physical object properties is very important. And it's also very hard, just like why vision is hard, right? Why vision is, human vision or any kind of vision is great, and computer vision is very hard to solve is because, going from a picture, right? There are infinite number of possible explanations about what's there in 3D. but we have a very good prior about what a thing could be like based on our knowledge, so that we can infer, in this high dimensional space, this very small low dimensional manifold that correspond to natural pictures and natural scenes and natural 3D objects. And the same for physical properties. The space of possible physical properties is very small. So if you just keep random sampling, right, it's not going to work. Even if you try a few times or try many, many times, it almost always gives you the wrong results. So how can we have a good understanding or estimation of physical object properties? Again, we go back to here. Now I'm in a second idea, right? Descending from diffusion or descending from pre-trained foundation models. So if these pre-trained, especially video generation models, can generate beautiful flowers and they all look pretty realistic, then they must have some knowledge about the physical object properties of, let's say, the stiffness of flower. So now the question is, how can I distill these physical object properties from a pre-trained video diffusion models? So in this work, actually, the way we did it is surprisingly simple. So it's very easy to explain. It was led by Samuel, who is an MIT PhD student. This is collaboration with MIT Bill Freeman, and Coleman, who is my PhD student. So what we did in this work is, you have some 3D Gaussians, right? So now this is 3D Gaussians. So Rob's the 3D Gaussian. You can render into an image. You can send the image into an I2V model, image to video model. You can get a reference video, right? So the reference video is supposed to be very realistic because it's video generation. It's going to only generate realistic stuff. But it's just a video. It doesn't tell you anything about physical properties. At the same time, in addition to the Gaussians, which is mostly for appearance, you also have a physics field. In this particular case, the physics field is mostly for Young's modulus. Later, we generalize it to model a lot of different things. In this very first attempt, it is just Young's modulus, the physics field of Young's modulus. We then go through differentiable physical simulation. In particular, we use differentiable material point methods, which is pretty popular in computer graphics in the past 10 years, mostly because it's nice integration with neural networks. And also it has some nice integration with 3D Gaussians because it's a particle. You can see it's a hybrid particle and grid-based verification. So it has some natural connection to Gaussians, but that's not very important. But think about it as just a differential simulation. Like you can have this physics estimation, you have the geometry, you let it go through differential simulation, differential rendering, and you can get a render video. As I said, your initial guess of the physical properties are probably not going to be very accurate. So you can get the rendered video or simulated video to be pretty unnatural, right? Objects going to bend in weird ways. But now you have a reference video. So what you can do is you can compare the two. You can compare the reference video and the render video, and now you get a loss. And it turned out that even if you just directly compute the loss in the pixel space, you get an L2 loss in the pixel space. And you go through backpropagation because rendering and simulation themselves are differential. So it goes through backpropagation to directly optimize and update your estimation of the physics field. It actually gives you a pretty good estimation of what should be the Young's modulus of the entire field, right? So just by changing the physics field so that it matches the reference or the guidance provided by image to video generation model. So now you can gradually update the physics field until you get a good estimation so that the rendering or the simulation becomes as natural as possible, right? So now you have a good understanding of physics, you can apply different actions, right? Think about how the scene will respond to your different actions. So here are some more results. You can deal with flowers, but you can also deal with a lot of different other types of objects. Because NPM, the material point method, the simulation method we use is mostly is the best when it works with soft bodies. So we have a lot of results on soft bodies like plants, heads, cables. Yeah. We can even compare with ground truth. So the first column is ground truth, which we got by putting a fan next to the object. So you can see, again, the PowerPoint artifacts is annoying. But you can see, if I have a fan, how the object is supposed to react to the external actions. And the second column is our model output. You can see our model output is closer to the ground truth, much better than the baselines, which do not have a good understanding of the physical object properties. Okay, so later, Coleman and another of my PhD student, Yue, they thought about, okay, can we generalize to other type of objects, not just work with soft bodies? So in particular, they look into fluid fields. So what is going on here is you have a single video of a fluid field, and you want to reconstruct a fluid field in 3D so that you can model actually now 4D, because 3D over time. You model the 3D fluid field over time, including both its appearance, how it will look like, and transparency, but also its physics. In this case, the physics is the velocity field of the 3D fluid, so that you can render the 3D fluid field, over time and see it from different viewpoints. You can also do different types of action condition predictions, such as, what's going to happen if there's wind coming from the left, right? So you can see how the estimated fluid field is able to respond to these actions. So in this work, we actually use a bit more of diffusion parse and diffusion guidance. We incorporated video models in several different stages of the method, which is the pipeline becomes a bit more complicated. But happy to talk about this offline because that itself I can spend another 30 minutes on it. Okay, finally, let me wrap up by saying, we try to, in this final project I'm going to talk about, we try to integrate and have a system that work with the diverse physical phenomena in the real world. The real world is not just like rigid bodies or flowers or soft bodies or fluid. It really has the integration of all these different types of objects. Rigid bodies interacting with soft bodies, interacting with fluid and sand, and so liquid, right? So all these different things. So how can we have a system that are able to simulate and model the physics, from let's say a single image or a single video, and create a 3D interactable world for objects of different matters. So this was built on the earlier work that we did called Mono World. So what we did in this work is it is a real-time user interactive 3D scene generation system. You can upload a single image, and user can say, I can upload a picture, and I can type in navigation commands. I can go to left and right. I can type in the things I want to see. For example, here, I want to go to the left, and then I want to see some imperial garden or Asian marketplace. So the system is able to, in close to real time, respond to your instructions and navigation commands and generate the scenes to be 3D consistent. So it's 3D, so you can go forward, backward. And also in close to real time, you can also say on the right, I want some cyberpunk city. So it's very different. So you can put everything into this one connected 3D scenes. But everything here is static, right? There's no dynamics. So how can we bring back the dynamics, the fluid simulation, soft body simulation, all these things into this interactive navigation or exploration framework? So the final problem I want to address is you want to go from a single static image and into interactive 3D scenes. So you can apply 3D actions onto the 3D scenes so that you can drag this rubber duck down, which itself is close to a rigid body, but it can interface with, for example, fluid. So let me show just a teaser video of what we did in this work, which is called Wonder Play. I think Meng Yu also mentioned. Yeah, so I think it's pretty self-explanatory. So I'll just first play it. You can apply different types of 3D actions. I think I want to emphasize that in this work, we still maintain an underlying 3D representation over time. So it's like 4D representation, which allows you to not just render a video, but also see that scene from different viewpoints, right? So you can also move the camera because you have a 4D representation. You can not only produce a video, you can move the camera and see, okay, how the scene will look like from a different viewpoint. Yeah, this one is, you can see the camera movement, right? You can see there's a depth occlusions and, this occlusions. Yeah, you can see that, yeah, in this work, because it's no longer object-centric, so the system, finally, the rendering method, it takes up a few things. One is the shadow. The second is, interaction between liquid and rigid bodies, and also the glasses now can break into pieces because we don't have an object-centric representation anymore. It's just all pixel-based. It's a particle-based, and you can render into pixels. Okay. So the main idea here is, sort of similar to what I have explained before. First, want to use kind of physical simulations, but they're not sufficient, right? As I said, they have a lot of issues. One is there are a lot of things that we don't know how to simulate, right? And second, even if you have a perfect state estimation, and second, state estimation is very hard, right? We spend all the time talking about how we just get a good estimation of Young's modulus or stiffness of a particular type of objects or velocity. But there are so many physical properties And vision itself is hard. How can you get geometry, right? So all these problems are very hard. So perception is hard. Even with perfect perception or state estimation, simulation itself is hard. So if you just want to use physical simulators, you have a lot of constraints. But physical simulators does have one good strength. That is, it does allow action condition predictions, right? It's fundamentally built for that way, right? It's fundamentally built to take current state and actions as the input and simulate what's going to happen in the future. At the same time, you can have video generation methods. Video generation methods, in some sense, are pretty complementary because video generation methods, they are supposed to be very general, right? If you go to GPT and type in any type of language, it's going to generate some beautiful videos. And it captures the visual priors so that even from a single image, there's a lot of missing information, occlusion, everything. They can try to compete it, right? It can capture these good visual priors. But the fundamental limitation, at least so far, maybe in 5 years or 3 years, this will change. But right now, they still cannot take actions as input, right? So what are the input that these video models can take so far? If you look at GE3 and all these models, then one is language. Language is in some sense kind of, you can think about it as a very coarse action, but it's not really actions. And second is often they can take a little bit of navigation command. We can say going forward, going backward, turn left, and turn right, right? So these are like very simple actions that these models can take, but it's not the real actions, right? So if I have to, if I'm a robot, or if I'm doing some here, and I guess you're experts in biology, medical experiments, or you're doing surgery, the type of actions that we're going to apply to the scene is very subtle and very complex, right? So can you imagine I'm going to teach a doctor to do a surgery just by using natural language, right? I guess that's impossible, right? If I'm just I'm a doctor and someone tell me, please do this and that, just doing based on natural language, it's almost impossible. You have to go there and see because there are a lot of things that you cannot really describe for the subtle actions, right? So for video models, they definitely cannot take these kind of very subtle actions as input. All you can take is language and go forward, backward. So now you can see they're really complementary at this moment, right? So our idea is, can we actually try to integrate them so that we have a hybrid visual physical generative simulator? So if we go back to this earlier paradigm, then I said, and the first idea is I use them as intermediate representations, and the second is I want to distill them, right? So now I'm trying to say is maybe there's a way of integrating these two ideas, right? So on one hand, you have these video models and try to get physical properties out of it as much as possible. Second, once you have the distilled or estimated physical properties, basically they can be used as conditions so that allows you to better control and interact with these video models, right? So that really helps you to close the loop. So going back to the Wonder Play example, right? The way we did it, still at a relatively high level, but I think it gives you a rough intuition about how this is done. If I have an input image, I want to build this hybrid generative simulator that has an integration of a physical simulator and a visual generation method. The way we did it is we first turn an image into 3D, maybe using our Wonder World, whatever earlier framework, which itself is not going to be perfect. It's going to have a lot of artifacts or missing information, occlusions are not going to be fully completed. But you can still send it to a physics simulator, which again itself is not going to be perfect. So you're going to have imperfect 3D reconstruction plus imperfect physical simulation. So that's going to give you some kind of simulation results, which in some sense you can think about it as you have a rough intuition about how the scene is going to behave, right? So you can see all the smoke. I can imagine if there's smoke wave coming from the bottom, then the smoke is going to go up. But you can see very clearly there are a lot of artifacts, right? First physical simulation is not not fine grained, and second, even visually there are a lot of artifacts. But these intuitive or coarse physical simulation can now be used as a guidance or condition. So basically, we extract optical flows as the condition for a video generation method. So the video generation method is going to generate a beautiful video, which is supposed to look perfectly realistic. Condition on the guidance of the physics, right? So if this is how the object is supposed to move, then this will be a beautiful video that align with the object motion. But it's just a video. It doesn't tell you anything about object geometry or physics. It's just a video. So the final step is there's some relatively complex optimization that we can do that allows you to refine the physical simulation so that they look like the underlying 4D representation, so that they match the observations from the video generation method, possibly from multiple different views. So by matching the physical simulation output, physical simulation state, so that the output matches the output of the video generation methods, allows you to now have physical simulation look a lot more realistic, right, closer to the video generation method. But also because then you still maintain this 4D underlying representations, right? So you can move the camera. So it's not just a video. You can move the camera, right? See it from different viewpoints. And also you can do action condition predictions. You can imagine how it's going to look like if I apply different actions on it, right? So it's not just a video. You support action condition generation. It is visually realistic. It is also supposed to be still physically possible because you have this underlying 4D representations, which is compatible with the physical simulator as well. So here is some raw results. You can see we have interactions with objects of different matters, rigid bodies with fluids. Here as well, the flow can go up and you can drag the shoes around. You can see how the shoe is going to disturb the fluid, or rigid bodies interact with each other, dealing with sand, soft bodies, and stuff like that. Action condition generation. You have a same scene, so you can apply different actions, and you can see how the scene is going to behave differently. Okay. So this was again led by Jiajun, who is my PhD student, and Coleman. They're both my PhD students. Yes.
You could train limited number of actions, or you can do all kinds of actions to.
The action condition prediction for fundamentally eventually is taken care by the physical simulator. So it doesn't matter what the actions are. You can specify an action representation is a force field. So you can specify any actions you want in the form of force field in 3D, and then should be able to apply it to any. And finally, we have two extensions here, but I only have time to just show one slide for one of them. Is we also most recently we did some improvements so that the underlying physical states, 4D states, become much more consistent, in both space and time, which means now you can apply multiple steps of interaction, different steps and of a much longer time horizon. But also, you can change the viewpoint to a much wider baseline so that you can move the camera around. Again, these are proper heights. So now you can also move the camera by a lot. You can see it from, even totally from the back. So it really improve the persistency of the underlying 4D state representations. Okay, I'm out of time, so I'll wrap up saying, we have been trying to understand, model the 4D world by building machine, not human, machine visual intelligence. And of course, we want to use these foundation models, right? Perception vision models and data-driven methods. But we also want to think about what's the role of, physical object properties and simulation, how they can play and how they can interface with these perception models, data-driven methods, right? So the fundamental question we always want to address is how you can balance data learning versus modeling, right? To ask the question about what needs to be modeled, how does it help understanding, what's the role of physics, and what's the role of foundation models. And so I think in some sense, we can say you can summarize the things I've been doing as we want to do visual understanding based on these causal, physical, and universal object intrinsics, because physics is very universal, right? It's also fundamentally causal, which is very important because that's how you can build these simulators. It's causal in the sense that you can apply different actions and it's supposed to respond to your actions. So that gives you all these nice properties. But specifically how these intrinsics can be integrated, we showed a few different ways, right? One is putting into your learning systems that has some benefits, but also has some constraints, or maybe using them as distillation targets, right? Trying to distill them out of the learning systems, or some hybrid, some integration of the two. So it allows us to build on top of the data-driven methods, which has been trained on in the wild images and video data and language data, but also allows you to get the power or the strength of physical simulators and potentially synthetic data. And these physical object properties or intrinsics naturally serves as an interpretable interface that allows you to easily interact and control these generative models so that you can control it not only through natural language, you can now control it through physical properties or actions and different things. And which we haven't shown, but we have shown, but I don't have time to talk about it in this talk. What we have been also working on is how especially these action condition predictions enable a lot of applications, especially in robotics. Yeah, thank you. Great.
Any questions?
That's great. So that I can go to the airport. Yeah. Yeah. Thank you. Yeah.